I'll be talking through the solutions to question 1 from the 2015 exam for the unit numerical methods for partial differential equations. So the first question is all about hyperbolic PDEs and their solutions. So for question 1a, you're asked to write a brief explanation of domain of dependence and range of influence. Well, the domain of dependence is just all points for which has an effect on our point at time t and space x. So u is a solution at time t and space x. All those points which have an effect on that solution are in the domain of dependence. And the range of influence is similar, except for this time we take our point at time t and space x, and the set of all points for which our point has an influence on is in the range of influence. So this can be shown in the diagram for part B. Okay, so here we have x, the spatial domain is along horizontal axis, and vertical domain is a time axis. So as we go up the vertical axis, we're going forward in time. And in the middle, here's our point at time tn and xn. So all those points which came before it within this triangular region here have an effect on our point. So this is the domain of dependence, and all those points in the future which our point has an effect on is the range of influence. Okay. Notice that we have sort of this triangular shape for both domain of dependence and range of influence. This is because this is the maximum advection speed for permissible by our equation. So anything outside in this sort of area here, and the reason why the point up here wouldn't be in the range of influence is because the fastest possible wave wouldn't have reached that point yet. Okay, part C, you're presented with the Latz-Friedrich scheme and you're asked to show that it's consistent. So what we do here is we replace all the u terms in the scheme by Taylor series. So the ui n plus 1 means step forward by one time step. So there we have a forward Taylor series in terms of t. And I plus 1 means step forward one spatial step. So there we have a forward step Taylor series with a forward step in terms of x. And similar for I minus 1. Okay, so you replace the Taylor series or your u values up here with the Taylor series. Do a bit of cancelling out. And we get down to this expression here. As you can see, we've still got delta t's in here. Okay, we're going to make an assumption, but our spatial step is, well, equal or approximately equal to the error for a first order Taylor series. So if we do that, it cancels out the delta t's, so we're left with our advection equation plus the truncation error. Okay, this error is first order in time and first order in space. Okay, second part of this question is use a von Neumann stability analysis to show that the Latz-Friedrich scheme is stable for values of c is less than 1. Okay, and it says you may find the following useful. Well, this is sort of essentially a Fourier node, and what we do is you take your u values from your scheme and you replace them by this Fourier node, and if we do that, we get this expression here. Okay, and we can simplify this by dividing throughout by this term, and we get this expression. Now this e to the a delta t, this is an amplification factor. This is how much our errors grow over a single time step. So we needed this amplification error, and we call it g here, to be less than or equal to 1 in order for our scheme to be stable. Okay, so what we need to do is find this value for c where this whole right hand side is less than or equal to 1. Well, to get rid of the imaginary values, so you can see we got these values I, which are the square root of minus 1. Okay, we can substitute in the trigonometric identities, sine and cosine, and so g is equal to the cos k delta x minus I c sine k delta x. And for stability, the magnitude of this right hand side is going to be less than or equal to 1. So if we square both sides, 1 squared is 1 obviously, as you can see there. If we square each, we're calculating the magnitude or modulus of an imaginary number or a complex number. If we square the real term, we get cos squared k delta x, which is going to be between 0 and 1 for whatever k or delta x is. Because we got I squared, that becomes minus 1, but minus 1 times that negative becomes positive. Sine squared is between 0 and 1, and c squared, well, that's going to be a positive number as well. Okay, but what we have is, because cos and sine are a phase out by pi over 2, okay, so cos squared plus sine squared, okay, is equal to 1, well-known identity, therefore c must be less than or equal to 1. So this shows that the Latz-Friedrich scheme is stable for values of c less than or equal to 1. Okay, part D, asking you to apply the Latz-Friedrich scheme to solve the advection equation. Okay, so your domain is 12 meters in length with a flow velocity of 2 meters per second, and we have an initial profile given by this case statement. So where our x coordinate minus 5, and take the absolute value of that is less than or equal to 1, we have an initial value of 1, else it's 0. Okay, so the domain is discretized using 10 finite difference nodes. Calculate the maximum allowable time step. Well, this is something you'll need to remember, but in general, the maximum allowable time step is your spatial step divided by the magnitude of your velocity. Okay, and this is what's known as the CFL condition. Okay, so our spatial step, if we first calculate that, it's the domain length divided by the number of nodes minus 1. Okay, so in this case it's 4/3 or 1.3 recurring. Okay, so therefore 4/3 divided by the magnitude of the velocity, which you're told is 2, gives us 2/3 or 0.6 recurring. Okay, the next part of that question involves editing the program advection.m, okay, by replacing all the question marks with appropriate commands. Okay, so I'm just going to bring in our advection.m. Okay, so here we have. Okay, so you can see here we've got some question marks. So the number of nodes we can change to be 10. Okay, our domain goes from 0 to 12, so it's a 12 meter stretch. Our velocity was 2. Our time step. See if the question asks us for a specific time step. Yes, it did. So the question asks us to use 0.5 as the time step, and the number of steps. So what the question asks us to calculate the solution when t is equal to 2 seconds. Okay, so we're going to have essentially 4 time steps. So 2 divided by, so the time which you want to calculate the solution for divided by the time step. So it's just going to give us 4 steps. Okay, the next step is to find the initial conditions. Okay, so our initial conditions were zeros everywhere. Okay, so I've created an array of zeros, so that's, where's that case statement? Here we are, so we've got zeros everywhere, and I've created an n+2 array of zeros. The reason why it's +2 is because we're going to have 2 nodes, one either side of the left and right hand boundary, so those are our ghost nodes, so I've added 2 to n. Okay, here we have, for when the absolute value of x minus 5 is less than or equal to 1, our initial condition is 1. So I'm going to just say, okay, so absolute value of x minus 5 is less than or equal to 1. Okay, so then that's our initial condition. Okay. We scroll down, the next thing we have to change is the to actually calculate the scheme. So if I scroll up to the Latz-Friedrich method, here we are. So the ith node, so all I'm going to do is write the command to compute the solution for the ith node. Okay, so that's a half times ui plus 1 plus ui minus 1 minus velocity times delta t over 2 times delta x. And that's multiplied by the solution at ui plus 1 minus ui minus 1. Okay. Right, so what I'm going to do now is just press the run button and see if it works. Okay, so it has worked and it's produced this plot for me. So you can see, but the red line is the initial conditions and the blue line are our computed solutions. Okay, the question, if we go back to the exam paper, if I go back to the right question, it says write down the computed values for you when t is equal to 2 seconds. So if I bring in the command window and find out what the values of u are, these are the solutions which you should be writing down in your answer booklet, as well as, of course, saving the MATLAB file to the H drive. Okay, so those are the solutions there, and you can see that's what I've written down. Okay, you might notice I haven't included the ghost nodes. Doesn't really matter if you do or you don't, so don't worry about that.